네, 그럼 이제 슬슬 시작하는 게 좋을 것 같습니다. 예, 이제 한정훈 교수님, 예, 들어오셨네요. 네. 교수님 안녕하세요. 네, 그럼 이제 시작하도록 하겠습니다. 지금 보니까 외국분이 한 분도 안 계셔서 일단 소개는 한국말로 드리고,
네.
그다음에 이제 교수님께서 아무래도 이렇게 편하신 언어로 이렇게 진행을 하시면 될 것 같습니다.
예,
네,
그렇고요.
오늘 연사분은 UC 데이비스의 김한영 교수님이신데요. 간략히 교수님 소개를 드리도록 하겠습니다. 김한영 교수님께서는 이제 칼텍 존 프레스킬 그룹에서 이제 박사를 하셨고, 그 후에 박사를 마치시고 이제 여러 좋은 곳에서 이제 박사후 연구원을 하셨는데, 페라미터 인스티튜트, 그다음에 이제 IBM, 그다음에 이제 스탠퍼드 유니버시티에서 이제 박사후 연구원을 거치시고, 그다음에 유니버시티 오브 시드니에서 이제 시니어 렉처로 잠시 계셨다가 이제는 UC 데이비스의 이제 패컬티 멤버로 계십니다. 네, 김한영 교수님께서는 이제 여러 분야에 걸쳐서 되게 폭넓게 연구를 많이 하셨는데, 예, 최근에 주된 연구 분야는 이제 퀀텀 매니바디 피직스와 이제 퀀텀 컴퓨테이션 분야인 것 같습니다. 최근에 되게 재미있는 연구를 하셔가지고 제가 이제 세미나를 부탁을 드렸는데, 오늘 이제 모듈러 커뮤테이터와 컨포멀 필드 티오리 사이에 아주 흥미로운 그런 물리에 대해 이제 얘기를 해 주시겠습니다. 예, 환영의 박수로 맞이하겠습니다.
감사합니다. 그럼 영어로 해도 됐죠?
네네.
네. 그러면은 시작할까요?
네.
네. Okay. Thank you for inviting me. I will be talking about two works. So these are my collaborators, and in these two works, we defined what we called as modular commutators, and we computed this quantity in two different kinds of physical systems. One is a 1+1D CFT, and the other is a 2+1D gap systems. And I'll talk about these calculations and its physical meanings in this talk. And if you have any questions, you can ask me during the talk. So this will be a talk about entanglement in quantum field theory or quantum many-body systems. And as you may very well know, for the past 10, 20 years, people have been thinking about this a lot. And the usual setup is that you have some quantum field theory or many-body system, and you consider some subsystem, let's say A, and you can imagine having many, let's say, like quantum spins here or like fermions. And what you do is that you calculate the what's known as the entanglement entropy of a subsystem A. So here, rho is the density matrix, and rho A is the density matrix of the subsystem A, and this is known as the von Neumann entropy of rho. So you can calculate these things, and oftentimes what people found out was that when you do the calculation, you often have a leading non-universal contribution, which is not very interesting, but often the subleading contribution is universal, and it basically only depends on what the underlying phase is. It doesn't really depend on the microscopic details. So this has been one of the major driving forces of theoretical physics for the past 10 years. And in this talk, we're going to talk about a slightly different kind of entanglement measure called modular commutator. And I wanted to introduce it in such a way that it's somewhat similar to entanglement entropy. So one way to think about the entanglement entropy is to view it as an expectation value of the log of the rho A. So let's say I want to compute the entanglement entropy of subsystem A. This is just a formula, and we can just rewrite things in a trivial way. And this bracket just means the expectation value in quantum mechanics with respect to some global state. So entanglement entropy is really just a expectation value of the log of the reduced density matrix. So of course, you can define other objects. You can consider linear combinations, but that'll be just linear combination of entanglement entropies. You can consider some higher order terms. For example, you can have two subsystems. So let's say I have X here and Y here. And instead of computing expectation values of log row x and log row y. I can calculate the second order correlation functions. And you might ask, like, what are you going to get? Maybe this is a very naive question, but at least this is a one way to arrive at the definition of the modular commutator. Okay, so the actual definition of the modular commutator is slightly different. So we don't quite compute the product of the log of the reduced density matrices. We take the commutator. We take the commutator of the two, and then we take the expectation value. I think there's some feedback a little bit, but okay. So that is the definition. So the setup is that you have this many body system. You consider three subsystems, A, B, and C. Okay, and then I can define density matrix over AB and like BC. So here you see log of row AB and log of row BC. You take the commutator, and so you see the commutator here, and you take the expectation value. So why do I have the I here? It's there just to make sure that I get the real number. Of course, that's just a convention. And the reason why this is a real number is because this is Hermitian operator, so their commutator is anti-Hermitian. So
네, 간단한 질문이 하나 있는데요. 로 AB는 그 AB 안에서 하는 스테이트별로 그 로우하고 컬럼이 이제 레이블링이 되고, 로 BC는 BC 안에서 하는 스테이트로 이제 로우하고 컬럼이 레이블링이 되는 거잖아요. 그래서 저걸 곱해서 expectation value를 한다고 할 적에는 저 expectation value는 누구에 대한 expectation value고 곱도 어떻게 define 되는 거죠? 하는 스페이스가 다른 것 같아요.
All right, so the question is, formally speaking, this matrix and this matrix lives on a different space. So like, how is this actually defined? This is a good question. So I was a little bit sloppy here. If I were to write this correctly, the correct definition would be this. So what I left out was the tensor product and the identity.
네, 된 것 같습니다.
Okay. Yeah, this is the actual correct definition, but it's usually customary to just neglect the identity, so that's why I didn't write it down. But yes, okay. So that's the definition, and even before we go into actual calculations, there are some very interesting properties about this quantity. This is just quantum mechanics, by the way, no quantum field theory. The first is that it's anti-symmetric under the exchange of A and C. So you can see this very easily. So you exchange A into C, so then you flip the sign, so you get the minus sign here. So physically, that amounts to like flipping, like basically, well, it's like a parity transformation, like not quite, but basically the location of A and C has changed. So under that transformation, you get a minus sign. And another thing that is like less obvious is that if you take the complex conjugate of the global density matrix, then under that transformation, you also get the minus sign. So I should be a little bit more specific about this. So you might be wondering in what basis do I take the complex conjugate? So this is any basis in which you have any basis which is in the product form over A, B, and C. So let's say you choose whatever basis that you want, but you choose it in such a way that it's in the form of NA, let's see, MB, and MLC. And what these states N and M and L are, it's not important. As long as this is your basis choice, with respect to that basis choice, if you take the complex conjugation, then you get this minus sign. And at least for bosonic systems, you can think of this as a time reversal So it's so what I'm trying to say is that unlike the entanglement entropy, if you apply these operations, if you change like A and C or apply complex conjugation, the entanglement entropy will remain invariant. So that is even under these transformations. But this quantity is manifestly odd under those transformations. So that's something that is very different from normal entanglement measures. And I should note that this is not just about entanglement entropy. To the best of my knowledge, I do not know any entanglement measure that is actually odd under time reversal, at least for bosonic systems. So it's a very curious quantity. People didn't really use it as an entanglement measure because it can be minus. So it can be both plus and minus. So when it's minus, it's not entirely clear what that means. But it's pretty clear that this is something quantum. There's something quantum here, because if everything is classical, then you can just write the density matrix in the product basis. You can diagonalize in the product basis. And in that case, log row AB and log row AC can be simultaneously diagonalizable. So they will just commute with each other. So this will be trivially zero. So in order for this quantity to be non-zero, there has to be something quantum here. But the nature of it is not so clear. But at least the good news is that for interesting physical systems, you can calculate this thing and see what we get. Yeah. So I guess the surprise is that in many situations, the result of this calculation yields a very clean expression. In fact, in all the cases that we studied, we always got a result that is independent of the cutoff. This is very different from the entanglement entropy calculation, where you have a leading cutoff dependent quantity, and then you have the subleading term. Here, we don't even have this like leading non-universal part. It's just like universal period. And what surprised us was that the result of the calculation illuminates seemingly unrelated fundamental issues to this quantity, such as the sign problem in like quantum Monte Carlo, like fermion doubling and things like that. So I'll be talking about this in the future slides.
저 여기서 컷오프는 뭐 정확히 어떤 걸 말씀하시는 거예요?
그러니까 그 예를 들어서 그 lattice spacing 같은 게 안 들어온다고요. 그러니까
네. 네, 알겠습니다.
지오메트리가 저렇게 되는 게 중요한 거예요. ABC로 다 완전 딱딱딱 끊어져 있거나 뭐 이러면은.
다 끊어져 있으면은
저게 조인트로 있는 게 중요한지.
Okay, so the question was, is the choice of the subsystems important in making these conclusions?
네.
And I don't know, because we could only calculate these things in specific cases, and in other cases we don't know. So
네.
we don't know if we're going to get universal results. I'm actually curious, but I don't know.
그리고 하나 더 질문은 인탱글먼트 메저라고 하셨는데 이게 뭐 인탱글먼트 엔트로피처럼 뭐 이니퀄리티를 만족하거나 그러네. 아니면 그냥 인탱글먼트를 뭔가 디텍트한다는 센스에서 그냥 메저라고 부르신 건지.
Okay, so the question is, in what sense is entanglement measure? It's the sense in which it's non-zero only if there's something quantum here, but it's not very precise. Yeah. So we don't have any people call this operational meaning. We don't have any of that.
그리고 하나 더 질문 죄송합니다. 하원을 하나 더 올리면은 어떻게 되나요? 거기서는 뭐 특별한
so higher order terms we haven't studied.
아니 그 스페이스 디멘전을 하나 올린다 했습니다.
Okay. So well.
2 plus 0랑 1 plus 1만 집중하신다고 하긴 했는데.
So right. So this quantity will be so this is important. So you will right. So we expect when you calculate these things in quantum field theory, you're going to get something that is like obviously like odd under time reversal or parity, and the natural thing for that is the natural natural, like universal object that you can have in that direction is the chiral central charge, which you know, does well, okay, so I'm not an expert in this, so but I've heard that it cannot exist in like all dimensions. So I believe after 1 + 1, I believe it's
like 3 + 1, 4 + 1. 네. 그러니까 그 그래비테이션 아노멀리 있는 디멘전에서 비슷한 게 뭐가 있을 것.
Yeah, so it could be that in the absence of gravitational anomaly, you may not get anything. You may just get 0. Although we haven't checked. Yeah.
그거 재밌네요. 알겠습니다.
But that's our suspicion. Yeah.
네.
Okay. So yeah. So in the rest of the talk, I'm gonna talk about our roughly our calculations in two different parts. In part 1, I'm going to talk about 2 + 1D topological phases. In part 2, I'm going to talk about 1 + 1D CFT. And obviously, they are somewhat related to each other. But this was our first work. So a little background. I'm sure most of you are very much well aware of this. There's this famous quantum Hall effect. And one of the defining features of this is two-dimensional systems, two-dimensional electron systems. And one of the defining features is that you have the quantized Hall conductance, which is something that can exist in a system that has a charge conservation symmetry. But there's another effect which persists even if the charge conservation symmetry is broken. So even if let's say your only conserved quantity is the energy, even in that case, there is something quantized at the edge, and this is known as the quantum thermal Hall effect. And in short, physically, what this means is very simple. So let's say you have a two-dimensional material on a disk, and you push it, you lower the temperature enough such that the temperature is lower than the bulk excitation gap. Then at the edge, you're going to have a energy current, even though there is no charge conservation symmetry. And the expression for that energy current has a universal form. There's pi/12 times C minus, which is something that comes from conformal field theory, times T squared, where T is the temperature. And again, this is independent of the microscopic details. And the I is the magnitude of the energy current, and this thing is only determined by temperature and this value C minus. And an interesting side remark is that this C minus, even though it looks like it's something that only should be present at the edge, it actually has a pretty interesting connection with the data in the bulk. So again, imagine you have a 2D system. And it turns out that this C minus, chiral central charge, has relations to the quasi-particle data in the bulk. So there, I'm not going to go into much details here, but some of the data that defines the anyons are like quantum dimensions and the topological spins. These are some numbers. And these numbers, once you sum them over in some weird way, that should be related to this chiral central charge. So there is a non-trivial connection between this, what happens at the edge, and what happens in the bulk. In any case, in all these systems, it's a bit at this point, it's an old story that there are lots of topological invariants that characterize these systems. And one of the many interesting results over the past few decades has been coming up with these invariants and understanding them. So okay, so now getting more into the context. So one of the things that people started to think about in like mid-2000s was like, how can we extract these invariants from the ground state? And there has been some interesting work by these people who proposed to basically compute ground state entanglement entropy. And then people started to become more sophisticated. So people proposed to look at the entire entanglement spectrum. And people also proposed to compute the overlap of the different ground state wave functions, and that can give rise to these aforementioned data like dA and theta A, et cetera, et cetera. But and from that, you can determine this chiral central charge to some extent mod 8 if you know all the dA and theta A. And under some extra, using some extra tricks, you can actually make it a little better. But like somehow getting this value of like chiral central charge from the bulk in a more direct way has been somewhat it wasn't, I think it wasn't completely obvious, at least like if you're only restricted to the ground state wave function. So to that end, we propose a formula for this. Based on the numerics that we did, at this point, we like actually believe that this is really true because, but the formula is this. So maybe this diagram is a little misleading. So imagine you have this this square, right? So square is the physical system, and this circle is just a partition of a disk inside of the physical system, okay? And what the formula says is that in this 2 plus 1D gap systems, if you compute the modular commutator with respect to this choice of subsystems, you're going to get pi over 3 times a chiral central charge, okay?
이것도 모드 H인가요?
네?
여기도 모드 H인가요? C-가?
아니에요. So it's important to note that here C minus is not mod 8. So this is really like honest to God chiral central charge. And one way to see this, maybe it could be a feature or a shortcoming, but if you stack two things together, the modular commutator will be additive actually. So you'll not get any like mod whatever structure when you calculate modular commutator. Yeah, so anyway, so this was our proposal. So we had some derivations. I'm going to tell you a little bit about that derivation. But when we first, I should make a sorry remark. When we first proposed this, we only did calculation for some like fractional quantum Hall like wave functions. So we were like pretty size limited. So we are like reasonably confident that this is true, but like, you know, you could only go to like maybe like 30 sites or something. But then my other collaborators, he quickly made a code to test this for like the integer quantum Hall state. And for that, the error in this formula went down to like very small number, like 10 to minus 6, basically. So at this point, we did all sorts of things like adding perturbations and like adding disorder, and it's always the same. So I strongly believe that this is actually correct.
이게 펄미오닉 보존익 상관없이 쓸 수 있는 건 거죠. 그러니까
Yeah, so
보존이라고 계속 집중하셔서
it does not matter. Yeah. So it works for both bosons and fermions. Yeah. So yeah. So how is this formula derived? I can sketch you the basic ideas. So this is more of a side detour, but basically the way in which we arrived at this formula is kind of interesting, I think. So some of my collaborators and we've been working on this thing called entanglement bootstrap. Love to talk about it, but perhaps not so much in this talk. I'll just give you a basic philosophy behind this, and then explain why this can help us at all. So in entanglement bootstrap, you're sort of trying to solve these quantum many-body problems by making some assumptions on some bounded regions of this many-body systems. So you have these like 3x3 patches. So like imagine you consider subsystems which are sufficiently large compared to the correlation lengths. And on those subsystems, you assume that there is some lack of quantum correlation, which are motivated from known results in many-body physics. And starting from that, you want to basically very strongly constrain the form of the ground state wave function. And the surprising thing is that you get a lot of you can derive a lot of constraints from this, and that is sometimes so strong that you end up getting a result like this. which is a bit surprising. So basically, what we're imagining, what we do in this line of business is that we make some assumptions. So these are what we call as our bootstrap axioms. What it actually is not too important in this talk, but it's some basic set of assumptions that we assume on some like finite size systems, subsystems of a very large system, and we want to understand the consequence of that. So you might think that this is kind of very foolish because you're just assuming this is just some entanglement entropies, and like how can you expect to get anything? But surprisingly, you do get something. So for example, you can get the fusion rules of the anyons. So that's what we did in 2020. And you can extend this to the cases where, for example, you can have like gap domain walls between two quantum phases. And the surprising thing is that there you get some identities, which actually seems to be new. So this simple assumption seems to actually holding a lot of information, and we just need to unpack that.
여기서 이 엑시옴 전에 그 저기 인테그먼트 에어리어로가 만족이 된다라는 걸 사전에 가정을 하고 시작을 하는 건가요?
Right, so it's a good question. So are we assuming if the area law is true? And the answer is yes. So yeah, so if we assume that the area law is true, then the booster axioms are satisfied. And I think this is actually an if and only if condition. So if these are satisfied exactly, then the area law is also satisfied exactly. Yes. So it's, yeah, I think one can say that this is basically just assuming area law in a strong. Yeah. So, but in these past works in Entangled Bootstrap, we just we're very what should I say? We're very conservative. So we didn't make, like, aside from area law assumption, we didn't make any extra assumptions. One difference in this work is that we made some extra physical assumption, namely that if you have this 2 + 1D system at the edge, you're going to have this energy current, and that energy current will obey this universal formula. So that is a non-trivial input, another assumption, and that's how we basically arrived at this formula. The reason why this could work at all is the following. So the first key is a concept called conditional independence. So at the end of the day, what we're trying to do is to constrain the form of the ground state wave function so much so that we can somehow arrive at this identity. So here's a question.
Yeah. So this formula applies to some finite temperature thermal transport. So why does that have anything to do with probing the ground state entanglement?
Right. So this formula holds for ground states in the bulk of the 2 + 1D system. So and this C- is the same C- that appears at finite temperature at the edge.
Yeah, I understand that, but then how does this universal formula play a role in deriving the final result at the bottom of the page?
So I think I can give you a short answer to this, and then fortunately the next slides will expand upon this. The idea is that I will do the following. So this is a 2 + 1D system. Imagine I cut off the part of the 2 + 1D system this way. So this interior region, and let's call this as X. And let's formally write down rho X as e to the minus log rho X. Obviously, I didn't do anything fancy. The key point is that these assumptions allows you to rewrite log rho X into a sum of local terms. So you can actually write down log rho X in terms of reduced density matrix over smaller subsystems. And that, the log of the reduced density matrix of the smaller subsystems. And let's think about how we can actually write down the energy, the energy current. Well, that's see. Let's say you have 2 points. Let's say U and V, and what's the energy current from U to V? That's basically I HU. So HU is once you decompose the Hamiltonian into a sum of terms associated to each site, I just write it as sum over U, HU. This HU is that local term. The energy current from, let's say, U to V can be written down microscopically as the expectation value of this thing. So you can sort of imagine that once you rewrite this as sum of some local things, you can compute the energy, quote unquote, like this is not the real energy current, but you're imagining hypothetically, if I were given this rho x, if I compute the energy current with respect to this rho x, what am I going to get? And the answer to the question will be of this form, and these individual HU will be the log of some smaller reduced density matrices. And that's where we use this universal formula. But maybe I should go to the slides because I was going to talk about that anyway.
그러니까 인탱글먼트 해밀토니언을 로컬 텀들로 쪼개고 그들을 가지고 엣지에서의 커런트를 계산을 해서 그 원래 포뮬라랑 비교를 해서 그 파이널 리절트를 얻으셨다는 말씀이신 거죠?
네, 맞아요. 네, 그렇죠.
네.
Right. So, okay. So why? I think then there are like two main questions. Like, how do you actually decompose this entanglement Hamiltonian? So just to be clear, by entanglement Hamiltonian, I mean the log of rho x. So how do you actually decompose that into local terms? That's the first question. And once you decompose that, how do you still there will be many terms. Like how do you actually carry out that calculation? So I want to address these two questions one by one. So regarding the first point, how do you decompose the entanglement Hamiltonian? The important thing is a concept called conditional independence. So this is just some quantity that is defined in terms of a linear combination of entanglement entropies. And what's important is that, first of all, in 2+1D systems, in many cases, this quantity just vanishes. An example of that is shown here. Let's say you have A, B, and C, then this quantity just vanishes. So what does that imply? It implies mathematically that so for any quantum state, if this is 0, you can decompose this log rho ABC into log rho AB plus log rho ABC minus log rho B. And notice that this implies that log rho ABC is equal to a sum of the entanglement Hamiltonians over smaller subsystems. So the basic idea is that you can decompose this large entanglement Hamiltonian of a large system into linear combination of entanglement Hamiltonians of smaller systems, and you just repeat this until your subsystems are too small, at which point it may be order correlation lengths, then this argument will no longer hold. But this way you can make a decomposed entanglement Hamiltonian of a large system to something to a linear combination of this entanglement Hamiltonian over smaller subsystems. So that's the basic idea. And the second idea is the modular commutator. Since we talked about the basic properties, let me just skip this part. Good. So by using these two facts together, what you can show is that, first of all, this JABC quantity is actually topologically invariant. What I mean by that is that notice that I didn't really specify the size of this disk or the actual the length of these individual lines. Basically, you can deform as you wish, as long as the topology of this ABC remain the same. So you can smoothly deform them, and one can show that under this deformation, the left-hand side is always equal to the right-hand side. So this is the first sign that we have a quantity which may be invariant. And more importantly, as I said before, we can decompose this modular Hamiltonian, entanglement Hamiltonian. Some people call it as modular Hamiltonian. And the way to do this is that, let's say you have some large subsystem, let's say A, and I just, for concreteness, like coarse graded into like smaller cells. And these individual cells, imagine they are like sufficiently large compared to the correlation lengths, but you know, they are, I guess, small compared to the size of A. And there are something that you can do. So suppose I have these, consider entanglement Hamiltonian over these 4 cells, okay? Then it turns out that by using this conditional independence condition, the entanglement Hamiltonian of this guy is equal to the entanglement Hamiltonian of this blue part, plus the entanglement Hamiltonian of this blue part, minus the entanglement Hamiltonian of this overlapping part. So do you see the pattern here? So the basic idea is that once you're given something that is large, I can decompose into 2 things which have some overlapping region that separates this part and this part. So this red part can be thought as a separating region, and the rule is that once you add 2 things together, you subtract the entanglement Hamiltonian associated to this intersecting region. So once you do that, you can write down rho A as e to the minus Ka divided by 1. 1 is just a number. And the energy current with respect to A should be, if you really believe in this formula, and this is an assumption, then this energy current should be pi over 12 times C minus times 1 square. The question is, this should be equal to something, and that something should be the actual energy current. So what is
temperature를 1로 셋하는 거는 ambiguity가 없나요? 그냥
right? So the question is there any maybe one can do something like this? Maybe I can do right. Indeed, so in that case, this will be 2 square, yeah. But on the right hand side, at the end of the day, what you're gonna get is you have a sum over some things, which is the expectation values of some commutators, and the factor of 2 will appear both here and here. So they will end up canceling out.
네.
Right. Yeah. So there will not be any ambiguities. So what is the so how do we what is the actual the energy current of this fictitious Hamiltonian? That's the question that we're asking at this point. And well, I already told you that the entanglement Hamiltonian of this large system can be decomposed into some of local terms, each of which are entanglement Hamiltonians of some smaller subsystems. Okay, so what I can do is that I should now try to calculate the edge energy current that flows between, let's say, from L to R. So pictorially, it'll look like this. So I should compute something that sort of looks like this. And what I can do, what I can try in the beginning, is to compute the energy current from this L to R. So L is this blue part, R is this green part. Okay. And what I would physically, what I would hope to see is that there are some energy current, roughly speaking, on this region, some place that is localized near the edge between L and R. Because if we really believe that the energy flows at the edge, there shouldn't be any like bulk contribution. So how do we do that? At least like microscopically, there's like a well-known like canonical procedure. So if we are given a microscopic Hamiltonian, what we do is that we rewrite the Hamiltonian in terms of a sum of HU, where U is an index for a site. In this case, it must be a cell. You just organize in this way, and you can define the energy current from U to V as the commutator. Sorry, I think I forgot the commutator. Commutator between HU and HV, and I guess I also forgot the I. So this is the energy current from U to V, and then you just sum over for U in L and V in R. So that's what you should do. And that what I think is really cool is that this calculation is actually doable, even though we made so little assumptions. And the reason why this is doable is because, as I said before, this JABC quantity is a topological invariant. And that's important because, for example, when we compute, let's say, commutator, the commutator between this one and that one. So to be clear, this is the entanglement Hamiltonian over this blue region, and this entanglement Hamiltonian over this red region. In this case, this will just become 0. And in this case, what do we see? So this is the situation that is similar to that. So let me remind you that J
저 여기 커뮤니케이터에서 하얀 영역은 뭐에 해당하는 건가요?
Oh, sorry. So the white region is basically for bookkeeping device, because if I don't have the white region, the relative location of this the red one and the blue one will be unclear. So this guy and this guy are the same cells. So yeah, but the white regions are not doing anything. It's just just to specify the locations. Yeah. Right. So yeah. So anyway, so the modular commutator between the commutator between these two things should be equal to the commutator between these two things. Why? Because you can see that, let me remind you that JABC is equal to I trace rho log rho AB log rho BC. So rho AB and rho BC. And okay, so there's a minus sign here. That's because you are in the opposite orientation. And you see that topologically, this quantity is actually just exactly equal to this JABC evaluated with respect to this partition. Just rotated by with an appropriate amount. And also topologically, this quantity is equal to that quantity because it's just the same shape. You can just deform this part into here and deform this part into here. So at the end of the day, once you decompose the this entanglement Hamiltonian into sum of HU and HV, for any U and V, this expectation value becomes some constant that only depends on U and V times JABC. And in fact, this constant is a numerical constant. I should emphasize that. This is a numerical constant that you can just compute. And so at the end of the day, you can compute the energy current as some numerical constant times JABC. Just from our assumptions alone.
저 numerical constant는 이 지오메트리에 의해서 결정되는 그런 벡터로.
네, yes. So one might ask, like, how is this numerical constant determined? It's one could say it's a it comes from the geometry, but I would say it comes from the following fact. So once you actually write down this decomposition, you'll see that there'll be some funny factors of like 1/3 and like one half, because we are organizing things in terms of sites. So there are some overcountings, so we have to weigh them appropriately. And these numerical constants are coming from these factors of 1/3 and like 1/2, basically. Yeah, so it's like a really trivial numerical constants. Yeah.
Excuse me. So are you saying that this equality is true for arbitrary mu and nu?
Well, since I haven't specified what U and V is, I guess yeah, but I am saying that this is true. Yes. So
well, obviously, you know, if mu and nu are very far apart, the commutator on the left-hand side will be 0.
that will be 0. Yes.
But if they're close enough, then
they are not. They're not necessarily 0. Then
okay,
it's something. Yeah. Yeah. I
see.
mean these numbers are not particularly clean. Individual numbers are not particularly clean. You get things like 5/18 or something. But in the end, once you sum them all over, you get a factor of 1/4, 1/4.
Okay, thank you.
Yeah. Okay, so that's how you derive it. But one thing that I want to emphasize, and I don't have an explanation as to why this is true, is that there is one potential caveat to this argument. So this is a subtlety that arises when you consider a lattice system. So in the continuum limit, in these 2+1D gap systems, obviously in the bulk, we don't expect there to be any energy current. But once you write down a lattice model, it could be that your decomposition of the Hamiltonian is weird, so that you get some non-zero bulk energy current. And you might think this is counterintuitive, but this could totally happen in principle. So what I tried to draw it right here. So what could happen is that maybe this is more of an artifact of a wrong definition, but maybe in your decomposition, you may have some bulk energy current, like here, around a very tiny region, and just like circling around on some like single site. And this could happen. But the thing is, in our calculation, we don't have any such contributions. They just happen to be 0. And I should note that this is not like trivial. It just, once you do the calculation, you can see that it's 0. But in the beginning, once you look at the theoretic expressions, it's not obvious why it should. Anyway, so the reason why I'm saying this is because we don't have to worry about this, because if there is such spurious bulk contribution, then the energy current from like left to right is not just coming from this edge contribution. They can be spoiled by this like a bulk contribution right here. And since we don't have that, we don't have to worry about it. So at the end of the day, once you do the calculation, you get this factor of 1/4, and you get pi/12. That should be equal to pi/12 times c minus times 1 square. So the conclusion is that JABC is equal to pi/3 times chiral central charge. One interesting remark that I would like to make is that let me remind you that this J quantity is odd under time complex conjugation. So yeah, so this, let's see, so if hypothetically, so what I'm trying to say is that if you have a chiral central charge of non-zero, then you have some serious difficulties in making quantum Monte Carlo to work for this system, because if you have some local product basis, which is like real, and not only positive, well, obviously you want the amplitudes to be positive, but like even before that, let's say you want it to be real in some local product basis. In order for that to happen, JABC must be 0, because if it's real, if rho is real, then under complex conjugation, the density matrix is invariant. So JABC rho star is equal to minus JABC. So if rho is real, this must be 0. So you can see that any ground state wave function, which under some local transformation can be mapped to some real product basis, must always have JABC being equal to 0. And since JABC is necessarily non-zero for this physical systems with chiral gapless edge, we should not expect to have any local transformation that lifts this, that removes this sign problem. I think it's, to be clear, this is not, we're not the first people who said this, but I think it's neat that there's a simple formula that shows this very explicitly. Okay, so I think I'm running out of time, but maybe this is a good time to pause and get some questions before I move on to the next part.
네, 제 질문이 있는데요. 그러니까 지금 여기서 말씀하신 JABC와의 하이럴 센트럴 차지 이 릴레이션십을 저희가 이제 실제 뉴메리컬 칼큘레이션 해가지고 한다고 하면 많은 경우 저희는 이제 레티스 모델을 가지고 이제 피리오딕 바운더리 컨디션을 적용해서 풀잖아요.
네.
그 말은 다시 말하면 이제 시스템을 토러스 위에서 올려놓고 이제 문제를 푸는데, 그렇게 되면 이제 토폴로지컬 디제너시가 발생할 거고, 그런 경우에 그 그라운드 스테이트를 어떻게 정해야 하는지 그 문제가 생길 것 같거든요. 혹시 이 부분에 대해서 좀 해주실 코멘트가 있으신지.
그러니까 만약에 이 ABC 그 리전 자체가 뭐라 해야 되지? 그러니까 그 non-contractible 루프를 포함하지만 않으면 상관은 없거든요. 근데 만약에 포함을 하면은 그때 어떻게 될지는 잘 모르겠네요. 그러니까 이게 그 토러스를 커버를 하면은 그 경우는 생각은 안 해봤어요. 그러니까 이게 기본적으로 non-contractible을 커버를 안 하면 그 어떤 ground state 섹터들든지 간에 전부 똑같기 때문에 상관은 없을 텐데요.
예. 컨트랙터블하게 그 디스크를 잡으면 그 토포로지컬리 디제너레이트한 스테이트들을 어떤 컨비네이션으로 잡든 결과는 같게 나와야 된다는 말씀이신 거예요?
네네, 그럼 같아야 돼요. 네. 최소한 크게 다르지는 않는데. 네.
만약에 값이 다르다라고 한다면 거기에 뭔가 파이나이트 사이즈 이펙트 같은 게 이제 껴들어와서 그런 걸로 생각을 하는 게 자연스러워요.
네. 근데 사실 그러면은 일단 이 모듈 커뮤테이터 문제 전보다도 이미 그러니까 사실 그러니까 그 이전에서는 전부 다른 섹터들 구분할 수 없어야 되잖아요. 그러니까 덴시티 매트릭스만으로는 사실 전체 non-contractible loop을 커버하지 않는 이상은.
네. 그래서
그거부터를 좀 확인해야 될 것 같긴 한데요. 네.
교수님, 여기 슬라이드에서 제가 살짝 헷갈리는데 민겔 페이퍼는 카이럴 센트럴 차지가 있으면은 그건 사인 프로블럼이 있다라고 스테이트먼트 하는 페이퍼고, 그다음에 지금 교수님 쓰신 거는 두 번째 문장은 똑같은 말을 하시는 것 같고, 그러니까 두 번째 if JABC가 논지로 오면은 사인 프로블럼이 있다라고 얘기를 하시는 것 같은데, 그거는 아래 거를 활용하는 건가요? 아니면 안 하는 건가요?
이거는 아래 걸 활용하지는 않죠. 그러니까 여기에서 잠시만요. 여기서 논리는 뭐냐면은, 그러니까 일반적으로 봤을 때 만약에 어떤 local product basis로 썼을 때 그 amplitude를 전부
리얼로 잡을 수 있으면은 짠 sign problem이
영이고.
없으니까 항상 non-decalable 하고, 근데 로우가 imaginary라고 해서 저게 논제로가 항상 나오네. 그거는
그건 아니에요. 왜냐면은 그러니까
그건 아니죠.
그냥 싱글 큐빗 그 유니타리를 모두 가해가지고 어떤
그죠.
네, 할 수가 있으니까.
그러니까 저 J가 논제로가 되게끔 만드는 거는 로우가 어떤 베이시스를 잡든 간에 뭔가 이미지너리 파트가 항상 있는 거고, 그래서 사인 프로블럼이 나온다라고 스테이트먼트 하시는 거고.
네, 그렇죠.
네.
Can we go back just one slide?
Mhm.
Yeah, so this formula on the left,
Mhm.
this bunch of commutators summed over, is that the boundary over some region R and the boundary?
Yeah. So I should be more specific. So over here, you have a sum over all the terms from left part and all the terms from the right part. But obviously, these are local terms. So if they are far away from each other, their commutator will be just 0. So here you can see, yeah, you notice right here, this is the boundary of R and boundary of L. And what I'm trying to say is that, yeah, you like when you actually do the calculation, the only only contributions which may not be 0 are concentrated in this region, which is near the edge and also near the intersection between left and R part. So there's like a constant number of terms, and I sort of skipped over this, but what I was trying to say was that you just need to calculate constant number of terms to actually calculate this instead of some extensive number of terms.
Yeah, but what I'm interested in is the fact that this commutator ends up being something like the amount of energy flow that crosses from one region to the other.
Yeah. Mm-hmm.
Yeah.
So that's an assumption. That is an assumption.
Yeah. But you're basically working under the assumption that this assumption is correct.
Yes. Yeah.
So
right.
somehow among these ABC regions, you're somehow calculating some sort of energy flow from like region A to C and C to D.
No. So right. So this how should I say? Maybe to put things in perspective, this is like a tiny thing. So the scale of these ABCs are like this.
Oh.
So so this ABC can be anywhere. Like what we're really doing is that this this quantity is related to something. So and this ABC, because this JABC is topological invariant, meaning that if we deform A, B, and C, this still remains the same. We can choose ABC to be this small thing over these regions. It doesn't even matter where they are.
Oh, I see. Okay, yeah, thank you.
Okay, so I will make this brief because of the interest of time, but I think I should really talk about this because it is a related story, and it's right. So we've been talking about the bulk of the 2+1D systems, but there's we we wanted to understand this from CFT basically, and there's a nice way to see that they're actually equal to each other. They're like related to each other in a very fundamental way. So for this formula, you're just gonna have to believe me, but it turns out that there's a equality based on just quantum information theory that relates JABC at the edge. So notice that here ABC is the edge subsystem, and XY of Z in the bulk, so X, Y, and Z. And let me remind you that in the bulk, the modular commutator is topological invariant. So this guy is topologically equivalent to that guy. So it reduces to the old formula. So, and the upshot here is that we know what the edge theory is. It's of this 2+1D system. It's a 1+1D CFT. So, and that's a very well understood quantum field theory. So we can just calculate things in various ways. So that's what we did. So like imagine you like zoom this out. So now you consider a imagine you consider only the boundary region. So assume that the boundary theory is described by CFT, and we're going to basically calculate the modular commutator by using there are various ways, but one reason to think that one could do this plausibly is because, for example, Calabrese and Hardy and like Tony, they discovered explicit formulas for the entanglement Hamiltonians. So like even in the worst case, you could just like plug that in and just do the calculation very explicitly. But there's a question of like what kind of density matrix should you use for the edge theory? And because the expectation is that the edge theory is a chiral CFT, there are actually like two natural choices. One is the choice in which you have only a left moving mode, let's say, and with a temperature of like beta. And the other possibility is that you have both the left moving mode and the right moving mode with the unequal temperatures, let's say beta left and beta right. And it turns out that they actually gives rise to different results. So if you do the calculation for the case in which you only have the left moving mode, once you do the calculation, you get the pi/6 C minus. Okay, but if you have the right moving mode, even if the right moving mode is like an infinite temperature, that still actually has a contribution, which sounds very weird because if you have some lattice system, this can never happen. But in CFT, apparently this is what it does. But only in that case, you get this pi/3 contribution, which is actually the correct one.
교수님, 근데 HL이나 HR은 시간이 별로 없으셔서 되게 좀 죄송한데 CFT가 정해졌을 때 CFT는 항상 arbitrary 이거 이렇게 C- 킵을 하는 상태에서 제가 arbitrary하게 더할 수 있잖아요. 그러니까 아까 말하신 것처럼 예를 들면 인티저 퀀텀을 여기로 도는 애 반대로 더한다든지 뭐 이러면 그래서 예를 들면 이 달을 제가 0으로 항상 보낼 수가 있는데도 불구하고 저걸 킵을 항상 해야 되는 건가요?
네, 그 킵을 해야 돼요. 안 그러면은 이게 그러니까 이 계산에서는 계산 결과가 잘못 나와요. 킵을 안 하면.
뭔가 좀 더 마이크로스코픽한 데이터 요구하는 것처럼 보이네요.
그러니까 이게 좀 특이한 게
어쨌든 뭐 속치가 별로 없으신 것 같으니까
네.
괜찮습니다. 시간 좀 충분히 가지셔도 괜찮습니다. 너무 서두르지 않으셔도. 네.
왜 킵해야 되는지만 짧게 말씀해 주시면 될 것 같아요.
그러니까 그 간단하게 말하면요, 그 이 예를 들어서 다음 슬라이드 보면 되는데 if you look at the most general expression, it looks like the following. So C left is the central charge for the left moving mode. C right is for the right moving mode, and you have this eta. So let me remind you again that we're considering a circle here, okay? And I'm considering a slightly different, slightly more general scenario in which A, B, and C is not covering the entire thing, but I'm allowing this extra region to be possible. So, and in any case, this is the formula that you get. So the thing is, even if the temperature goes to infinity limit, you like in that case you would. So what would be your intuition? So the intuition for like some lattice system would be that then you have a maximally mixed state. So that's like then you just have a uniform density matrix. So the modular commutator will be trivially 0. So then obviously obviously that will not contribute anything, right? But the thing is, when t goes to infinity limit, when you plug in this expression into here, you see that that contribution is not 0. And this is because you can't really just completely separate the holomorphic part and the anti-holomorphic part. You really have to add those up together to get the actual correct answer. And apparently in this case, this is important. And on a similar note, so this actually shows very directly that chiral CFTs are fundamentally incompatible with any lattice regularization, because even in the case where you cool it down to the ground state, so that you're in the vacuum, and let's say x1 is equal to x4, so A, B, and C covers the entire circle. In that case, if you assume any kind of tensor product structure, then you can very easily show that JABC must be always 0. It's some like very basic quantum mechanics calculations that you can just show, assuming tensor product structure.
그러니까 교수님 말씀은 혹시 1D에 제가 CL을 올려놔야 되는데 그러려다가 보면 어쩔 수 없이 CL이랑 CR이 다 있는 애를 집어넣어야 되고 그 다음에 이제 코렉트한 S를 뽑아내기 위해서 베타 L은 베타 R만 특정 리밋을 보내서 그걸 뽑아낸다.
네네.
오케이. 네, 알겠습니다.
Yeah. So
네, 죄송합니다.
So yeah. So what this shows is that but the thing is, for the theory with non-zero chiral central charge, this JABC cannot be 0. So what it means is that it directly shows that any theory with a non-zero chiral central charge, it cannot have any kind of like lattice regularization, because if it does, then you'll need to violate this thing. Again, we're not the first people who showed this, but I think the nice thing again here is that there's a concrete formula which shows very explicitly why this is not possible. Okay, one final comment. So it turns out that this formula that we show has a interesting geometric interpretation. So imagine you have these ABCs here, and I have these like 4 points, x1, x2, and x3, and x4. Imagine that you draw a geodesic from x1 to x3 and x2 through x4. Then there's a crossing angle between the two. It's called as theta. And it turns out that this quantity is actually equal to cosine theta. And our conjecture is that, sorry. So we're assuming that when I said geodesic, I meant the geodesic in the ADS space, in 2+1D ADS space. And the conjecture is that if you have a asymptotic in 2+1D asymptotically ADS space, JABC will be equal to this thing, the sum over cosine theta I. And of course, it's a conjecture, maybe it's wrong, but we've done some non-trivial checks already on the ground state, but also in the geometries with BTC black holes and 2 intersection points, et cetera, and so far it seems to work. Okay, so today I talked about this quantity called modular commutator. We only calculated this in like 1+1D CFTs and 2+1D gap systems, but already there, I think this calculation led to like pretty like succinct and clean expressions, and which very directly shows at least a lot of things that people perhaps knew, but I think in a more clear way. So I think that's very nice. That's it. there's some couple of questions that I'm always curious about. Mainly, like I don't know any situation in which this JABC is non-universal. So like in all the calculations that we did, we always got a universal result. So I don't know if this is a general thing or we just got lucky. And I guess I'll be curious to know if it will be possible to calculate these things in other interesting theories as well. Okay, yeah, thank you for listening, and sorry for running out of time.
흥미로운 톡 감사합니다. 네,
네.
아주 재밌게 들었습니다. 질문이 꽤 많았는데 더 질문이 있으신 분들 지금 질문하시면 되겠습니다. 질문이 없으시면 제가 하나 해도 될까요? 그 교수님 이거 이 포뮬라를 이제 numerical calculation을 통해서 이제 확인을 좀 하셨다고 하셨는데 결과가 있으시면 좀 보여주실 수 있으실까요?
네, 잠시만요.
네.
근데 지금 잠시만요.
네.
근데 지금 그 CFT 계산 결과는 있는데 그거는 지금 못 찾겠네요. 근데 코드는 있거든요. 근데 코드, 네.
그럼 말로만 그러니까 어떤 시스템에 대해서 이제
그러니까 홉스테더 모델에서요.
네.
보자. 한 사이즈가 얼마? 그냥 그림을 그려보면은 그냥 periodic boundary condition 하고 이 정도 되는 사이즈로 그 비교적 사이즈를 하면은 그래서 그러니까 정확히 이런 컨피규레이션으로 그냥 사각형으로 해가지고 제 ABC를 계산을 했거든요. 정확한 수치는 잘 기억은 안 나는데, 네, 그냥 네, 그러니까 모델은 홉스테더 모델이었어요.
시스템 사이즈는 대략 어느 정도?
그거는 제가 좀 찾아서 보내드리는 게 좋을 것 같은데요. 네.
네네.
네.
교수님, 또 제가 질문 너무 많이 해서 죄송한데 이게 센트럴 차지는 아시다시피 이게 카이럴이라서 상관없어요. 혹시 RG 모노톤인 것까지 보일 수 있나요? 네, 이게 토탈 센트럴 차지가 아니라 카이럴이라서 작동을 할지 모르겠는데 만약 카이럴 시어리면 RG 모노톤이긴 하니까.
네. 글쎄요, 그건 잘 모르겠네요.
그리고 다른 거 하는
그 C 디어럼 말씀하시는 건가요, 여기서?
네.
네.
그리고 다른 거 하나는 이게 우리 UV 컷오프 인디펜던트인지 잘 모르겠는데 핵가 나와서 UV 컷오프 인디펜던트 한 건가요? 저 J 안에? 그러니까 2+1 타원이고 로우가 3개가 나와서 UV 컷오프 인디펜던트 한 건지 그러면 그러니까 일적 결과 UV 컷오프 인디펜던트하게 나오잖아요. 인탱글먼트 탑이랑 다르게.
네, 그렇죠. 네.
그거를 미리 알 수 있나요? 그러니까 이걸 예를 들어서 하이어 디멘전에서 비슷한 포뮬러를 찾는다고 하면 제가 5개 넣어야 되는지 몇 개 넣어야 되는지 뭐 이런 것들. 그걸 잘 모르겠어요. 네. 그러니까 obviously는 이게 왜 UV 컷오프 인디펜던트한지는 틀려하진 않고 계산을 해보고 났더니 UV 컷오프 인디펜던트 하다. 그렇죠. 네. 아시겠지만 시메트리들이 들어가면 다른 거 하나는 이게 lattice regularization 안 되는 시어리가 되게 많잖아요. SPT, surface state들. 그런 것들에 대해서 제너럴라이즈가 좀 가능할까요? 뭔가 이렇게 클라인 바틀 같은 데 올린다든지 뭐 이런 식으로 하면 아비우스한 질문, 뭐 약간 나이브한 질문들인데.
근데 그러니까 일단 이 질문에 대한 대답이 될지 모르겠는데 그 컨스트레인 이 모듈 커뮤니케이터의 단점이 뭐냐면 예를 들어서 막 뭐 모드 8이나 모드 16 이런 스트럭처가 있는 인베런트들은 계산을 될 수가 없어요. 이게 그냥 스태킹 하면은 그게 그게 뭐 모드 16으로 이게 없어져야 되는데 이거는 컨스트럭션상 그럴 수가 없으니까.
네. 그리고 아까 논 유니버설한 넘버 나올 법한 시어를 여쭤보셨는데 논 유니터리 그 MPC 데이터를 만든 원비 체인 같은 거 하면 그 되게 이상한 CFT 리얼라이즈 되잖아요. 뭐 그런 거 하시면 나올 수도 있지 않나요?
그러게요. 네.
네, 막 던져봤습니다.
네.
이렇게 들었습니다.
네. 제가
다른 더 질문 없으실까요?
참고로 그러니까 시스템 사이즈가요. 그러니까 이게 정확히 그건 아닌데, 그러니까 최소한 CFT 계산에서는 한 뭐지? 아니다. 그냥 다시 제가 그냥 확실히 확인을 해서 보내드릴게요. 그건.
네네.
네.
이 시스템의 코릴레이션 랭스하고도 관계해서
예.
시스템가 주어질 테니까. 네.
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 저 질문 하나 해도 될까요?
네네.
네, 발표 잘 들었습니다. 제가 분야에 대해서 거의 잘 몰라서 그런데 여기 JABC 모듈러 콜레이터를 처음 봤거든요. 근데
네.
오퍼레이셔널 한 미닝이 잘 없을 수도 있다. 그러니까 아직 잘 모른다 이렇게 말씀하셨는데
네네.
보면은 그냥 쿠버 포뮬라 같은 데서 나오는 그 커뮤테이터 폼이랑 유사해 보이는데 그런 식으로 혹시 해석할 여지는 없을까요?
봅시다.
해밀토니안에서 퍼터베이션을 줬을 때 그 퍼터베이션에서 리니어 리스폰스를 어떻게 리액트 하는가가 사실은 커뮤테이터로 주어지잖아요. 그래서
네네네.
뒤쪽을 뭐 예를 들어서 퍼터비티브 해밀토니안으로 생각을 하고 앞쪽을 어떤 퀀티티로 생각을 하면은 비슷한 식의 어떤 관계를 볼 수 있지 않을까 하는, 그냥 저도 처음 하는 포뮬라여서 좀 그런 식의 해석이 가능하지 않을까 하는 질문 드립니다.
봅시다. 근데 그러니까 이게 제가 대답이 될지 모르겠는데 이걸로 잠깐 생각해 봤던 것 중에 하나가 그러니까 그러니까 홀 컨덕턴스도 이거랑 비슷한 포뮬라로 그러니까 찰즈 오퍼레이터도 넣어가지고 계산할 수 있을까 좀 생각을 해봤거든요. 근데 그렇게 하면 그러니까 그래서 쿠버 포뮬라 같은 그러니까 쿠버 포뮬라에서 그 해밀토니안을 그냥 인테그럴 해밀토니안을 바꿔서 계산을 해보려고 했는데
네.
그거는 잘 안 되더라고요. 근데
잘 안 하나요? 네.
네, 이게 제가 대답을 한 건 아닌 것 같긴 한데 그냥
네.
그쪽으로 말씀하셨으니까.
네. 아직까지는 뭔가 그렇게 명확한 그런 거는 오퍼레이션 미닝을 찾을 수는 없었다 이렇게.
네. 한
알겠습니다.
가지 제가 까먹은 건 있는데요. 그러니까 만약에 그 앞에 말한 것 중에 이게 이게 있었는데 그러니까 만약에 이게 0이면은 그러면은 이것도 0이거든요. 근데 그래서 그러니까 이 컨디셔널 매치 인포메이션이랑 상관이 있긴 한데 이 둘 사이 명확한 관계는 아직 잘 몰라요. 그러니까
네.
사람들이 추측하는 게 대략 어떤 이러지 않을까 생각을 하거든요. 여기서 C는 어떤 상수고요. 그러니까 뭐 파이 뭐 이런 상수.
아, 네네.
이건 아무도 몰라요 아직은.
아, 그러니까 그 0일 때 if and only if인가 아니면 뮤추얼 컨디셔널 뮤추얼 인포메이션 0이면은 커뮤테이터 모듈러 커뮤테이터도 0이 된다가 on if인가 on if인가.
if and only if는 아니에요. 그러니까 예를 들면은 이 density matrix를 그 리얼하게만 잡으면은 항상 J는 0이거든요. 근데
네네.
충분히
맞네. 그러네. 알겠습니다. 네, 감사합니다.
저 질문이 있는데요.
네.
그 모듈러 해밀토니안의 에너지 커런트가 원래 시스템에서는 어떤 의미를 가지는지 궁금합니다.
모듈러 커런트의 에너지가 원래 시스템에서는 글쎄요. 사실 모듈러 해밀토니안의 에너지는 그냥 인탱글먼트 엔트로피고 어떻게 글쎄요. 모듈러 해밀토니안의 에너지가 사실 그러니까 그거는 그러니까 제가 말한 시스템들에 대해서밖에는 딱히 얘기를 못 하겠네요. 그러니까 이렇게 계산이 되는 경우에는 그냥 그 카이로 센트럴 차지랑 연관이 있는데 그 더 일반적인 경우에 어떤지는 잘 모르겠어요.
네, 답변 감사드립니다.
네, 더 질문 있으신가요? 네, 없으시면 다시 한번 오늘 아주 재미있는 발표해 주신 그 김한영 교수님께 박수를 드리고요.
감사합니다.
이것으로 오늘 세미나는 마치는 것이 좋을 것 같습니다.
감사합니다.
네, 잘 들었습니다.
네.